Hello everyone. We're going to continue today with our notes on describing physical phenomenon. Last time we had defined how to describe location, change in location, and rate of change in location in terms of both scalar and vector quantities. Now we're going to focus on scalar motion only for a short time. So we're going to start with species of speed. And yeah, I know that sounds silly, but I had a college professor who did outlines for all his notes, and everything in the outline, like all the ones, the twos, the threes, the ABCs, they all started with the same letter. So it was, interestingly enough, easy to remember. So we're going to look at species of speed, which is scalar motion today. Next time we will look at varieties of velocity, the vector quantities. See what I mean now? Okay, so species of speed. We're going to start with constant speed. So when we describe speed with the adjective constant, that means the speed doesn't change its value. It is consistent rate of change of place or consistent rate of distance. And if we write that mathematically, rate, if you'll remember, we said is any ratio with time in denominator. So we're going to write a ratio, put time in the denominator, and how do we know that it's speed? Simple. We put change in place or distance on the top. So we can write it this way, or we can write it this way. Your choice. I've got the funny feeling you guys are more used to seeing this right here, so that's probably what I'll put up on the board. The units for speed are derived from two SI base units. The base unit for distance is the meter, and for time it's the second, and you're dividing. Of course, when we say it out, we say per for dividing, so we say meters per second, and we can write that as 1 ratio meters per second. So that's what would go at the end of the measurement. You can always determine the units for a given variable in an equation by looking at the other units to see what you get. Okay. So now what we're going to do with this constant speed formula is we're going to see what happens if we rewrite it a little differently. Suppose that we rearrange it by multiplying the v, or sorry, not the v, multiplying the t or delta t, the period of time, over onto the v. We get delta x equals v times t. Now, looking at the form of this formula that we've simply rearranged for the delta x, the change in place or the distance, we can see that this is a linear form of equation where the change in place would be the y, the change in time would be the x, and therefore the slope would be the speed. So the slope of a place-time graph is speed, okay? The slope is the speed, okay? Now, so what we're going to do right here is we're going to actually look at the place versus the time. Now, this is just a sketch. We're not really making a formal graph here, but it is a sketch. If we have an object that is traveling at constant speed, that means the rate at which we change place up the y-axis is always the same. So for each increment of time, we go up the same amount. So you would end up with a straight line slope, something like this. Now, this represents one particular speed. Okay, and if we looked at a different slope graph, we would get a different speed. But is it greater or less than? Well, the less steep the slope is, the smaller the value of the slope, and therefore the smaller the speed. So here, if we label these A and B, just keeping our colors consistent, then we can see that B would be greater than A. The speed for object B would be greater than the speed for object A. Okay? All right. Now, however, unfortunately for us, in real life, objects don't always have constant speed. Sometimes the speed changes. It can decrease in value or it can increase in value, in which case you would not get a straight line at all. You would get some sort of a curve, a changing slope to represent a changing speed. Let's suppose, for example, that you're on Manatee Avenue headed out towards the island. Now, you guys know as well as I do, and when you're on Manatee Avenue, there's no way on earth you're going to be able to travel at constant speed during the day. You've got red lights, you've got snowbirds pulling out in front of you or slowing down and slowing down and slowing down and slowing down and, to turn. So, what we have to look at when we're going out to the island, since we can't have constant speed, what we can talk about is your average speed. Your average speed. Now, you guys know the term average. This is what you use anytime you want to find your overall test scores. You take the number of tests you have and you add them up and you divide that by the number of tests you took and you get your average test grade. We could do the same thing. You could be driving along Manatee Avenue and have somebody sit in the passenger seat, and at every point in time, they could look over and write down the speed that the needle indicates on your speedometer. Every second, you write down one speed for that second, and you do this all the way out to the island. But now I want you to think about this a moment, considering how long it takes to get out to the island. How many speeds do you think you are going to have to average to get your overall average speed? Probably hundreds, if not thousands. That is rather, inconvenient to say the least. So, to get around having to add up hundreds or even thousands of different speeds simply to find the average, we can do it this way. We can take the total distance that we travel out to the island and we can divide it by the total time it took to get out to the island. That would average out all of the intermediate speeds for us. So, total distance divided by the total time gives you the average speed for the trip. Now, here's an interesting question. Where would the average speed on the above graph be? Well, whichever line you look at makes no difference, the blue or the red. If you want to find the average speed when you're traveling a constant speed, wouldn't it be the same value as the constant speed? Because at every point, the speed is the same value. So if you average them, you're going to get the same value. So it would be the same as the constant speed in this case. Now, if you had a graph that curved, the average speed would be found differently. In fact, if we make another set of axes, put t here and x here, let's say that you increased speed like this. To find your average speed, you would simply take the total distance traveled. That's what this is. The total distance and divide by the total time it took. And that would give you your average speed. In fact, what it would do is find the slope of this line. if you connect the beginning point and end point with a straight line and find the slope of that line, you will have found the average speed. Now that's kind of cool, isn't it? Did you know you could do that? Pretty slick. All right. One last species of speed we're going to look at. We've looked at constant speed and average speed. Let's look at this one. It's instantaneous speed. Instantaneous speed. Now, just like it says, notice the root word is instant right here. That's a given or one single point in time. Then your instantaneous speed is your speed at one single point in time. So we could come up here and look at any given point in time, look at the slope at that point, or if it's the one on the curve, look at the slope of that point, and you get your instantaneous speed. Now, interestingly enough, in your car, your speedometer gives you your instantaneous speed because the instant you look at it, it shows you how fast you're going at that instant. Okay? All right. So where would the instantaneous speed on the above graph be? All right. It would be the slope of whatever point you're looking at. Okay. So it would be the slope of whatever point you are looking at. Yes, I know we're not supposed to end a sentence with a preposition, but oh well. All right. Now, let's look at some ways we can use a a place versus time graph. Remember, we're using scalars here, so no direction is involved. Let's see what we can describe using a place time graph. Now, remember, all three types of speed are represented by the slope of the graph. All right? If you're looking at constant speed, you would have a constant slope. If you're looking at average speed, the slope is going to be changing, but you find this slope of the straight line connecting the beginning and end points. If it's instantaneous speed, you find the slope of that particular point in time. Now, let's look at an object at rest. How would we describe an object at rest on a place-time graph? Well, think about this for a minute. If the object is at rest, is it changing place? No, it's not. So whatever place you're located, it doesn't change that place during the time period. So the slope is 0, that means the speed is 0. So you get a horizontal straight line. Okay? 0 slope, 0 speed, because your place is not changing. Now, this one we just saw a few minutes ago. An object moving with constant speed. You would have some sort of a constant slope. So if the slope is constant, the speed is constant. Okay? And of course, as you know, the greater the value of the slope, the greater the speed. And that means the steeper the line will be. All right? We have just one more, I believe. So let's switch papers. Yes, just one more. We'll stop at varieties of velocity. Let's talk about an object with varied speed. Okay, you would get some kind of a curve. For example, if you have an increasing slope, you would have an increasing speed. But you could also have a decreasing slope, which means you have a decreasing speed. So when the slope is increasing, it's getting steeper, it's getting more vertical. When the slope is decreasing and therefore the speed is decreasing, it's flattening out. It's becoming more horizontal. Okay? All right then. So that's it for today's notes. Not too bad. I'll see you later. Bye-bye.